So I know that you are just like me. You are ready for these pieces and parts to be over with. How many more videos do we have to sit through in order to figure out how this machine works? So my answer to you is that there's just a couple left, and that's about it. So we need to go through and talk about some of the smaller things that I want you to be aware of when you begin to work with the TOC instrument. And the first one is this whole thing that we've been calling dilution water. Okay, dilution water in that schematic, and I'll pull that one up in just a second, but it's typically in the very beginning of the schematic near the 8-point valve. And we talked about the dilution water, and we talked about kind of the purpose of it at that time, and there's a couple of things that you have to kind of keep in mind. The dilution water is going to be used to make your standards, especially if you get the machine to make the standards for you. So this dilution water is going to be sucked into the 8-point valve. It's going to be sucked into that syringe, and it's going to be mixed before that sample gets injected into the machine. So this is a very important aspect of keeping my standards clean and keeping my standards organized and nice and tidy. That way I can get a really good calibration line from my detector at the very end of this process. So another reason that dilution water is used is also for a rinse. And we said that we can rinse some of these lines and rinse the combustion tube with distilled or deionized water. And all of that water will go in, flood the system, rush anything out that might be lingering behind that I do not want there. So this is also a very important aspect of keeping my system clean. So that way I do not have any carryover from one sample to the next. So dilution water is going to be used for a couple of different purposes here. Therefore, we need to talk about a little bit about maintenance of the DI water bottle. This is something that we've mentioned before in a previous video, but I never really told you any more details about it or how you should handle it or what you should do with it, right? We just kind of squeezed it into the schematic and said this is the purpose. So in the schematic, if I pull that up, this is what you've been seeing all along. At the very beginning of this instrument, near the 8-point valve, you're going to see tubing for dilution water. All right, and that thing is going to be right here in the very beginning. So this is where the DI water is going to be coming from. So therefore, we have to have a source with that distilled or deionized water in it that it can actually pull from. And there is something that's going to be there that we have on the side of our instrument. And we really already have seen that picture and that diagram before. All right. As far as the DI water is concerned, yes, we know why it's used and we know its purpose now. But some of the things that you need to walk away from, number one, you really do have to replenish this daily. It doesn't take very long. This jug is very easily accessible to you. You just unscrew the cap, you dump the water down the sink, and then you take our distilled or deionized water sprayer and you fill that jug back up to the top. This should be done in the early morning before people actually get to run it. And we want to do this every single day. Before we go through and begin to operate the piece of equipment. This just helps ensures that everything is staying clean again, and it's not going to take a lot of effort on our part. A lot of times when we start the machine up, this machine is going to take about 30 minutes in order to be ready. And the reason is because it has to work itself up to that 680 degrees. And that takes a little bit of time. So in that 30-minute wait period, what am I going to do? Am I just going to sit there and stare at the computer screen? And the answer is no. There are some things that I can do. One of the things is I can open the door up and double check the humidifier to make sure that those liquid levels are proper. And then over to the side of the instrument, I can go and I can take this distilled or deionized water bottle, I can take it off the machine, give it a good dump, give it a good rinse, and then fill it full of fresh water every single morning before I use it from that point on. So we want to make sure that this area stays clean, we want to make sure that this area stays fresh, and I never use soap. I only use soap when I absolutely have to. That's just a common thing that we do in a lab. Soap can begin to interfere with things. Soap can bring with it some ions, and we might not want that, right? And soap could maybe bring some organic carbon with it as well. I mean, we just simply don't know. So, in addition to that, I don't want sudsy stuff in my machine if you did not do your job and properly rinse these containers and this tubing out. So I never really use soap unless I absolutely have to use soap because it's that dirty. And if you're doing this every day and you are dumping the water down the sink and filling it fresh every single day, you'll never really need to use soap at any point in time because it's always staying fresh on the inside of that container. So we talked about the purposes of the water. You're going to see that it's used to rinse, and you're also going to see that it's used to make the series of standards that the instrument needs in order to pop you out a concentration or a number. This DI water bottle is going to sit over on the left hand side of the instrument for us, and it is a fairly large jug because this thing could use a lot of water depending on the number of samples and the number of standards that we have to make. As you can tell, there is a screw cap on the top of this jug, and that tubing line of course goes up into the instrument and down into the 8-point valve. So this area is easily accessible. You can get to it without a problem. It's just going to take a few seconds of your time to unscrew the cap, and then a few minutes of your time to walk it over to a sink, dump it, and fill it full of fresh water, and bring it back every single day. So here is the front of the instrument in the diagram. Don't let this confuse you. Right here is where the syringe would be, of course, right? And if you're looking at the front of the instrument, this water bottle is going to sit over to the left-hand side for you, okay? So here's a picture that I shared with you in an earlier video when we were talking about the auto sampler, and I told you that the auto sampler has a water jug that's associated with it as well. So we want to make sure that that one is filled and that one stays fresh, and the TOC also has one in addition to that. And you can see that one to the left-hand side of the machine. So if you look here, you can kind of see it poke out. Right there is my bottle that is kind of inset a little bit into the machine, and that bottle is filled full of distilled or deionized water. For us, of course, it's deionized most of the time. Deionized. Okay, so that's where the location of this jug is going to be. Again, easily accessible. It shouldn't take a lot of time on your part in order to do the maintenance that's required for that area. So there's the story with the DI water bottle that's associated with the TOC instrument. Another thing that's going to be located on the side, and of course we've talked about this before, is the hydrochloric acid. So the hydrochloric acid, I kept telling you, was part of the schematic, and I can bring that up again, and you see the acid intake line here. So there is a jug of hydrochloric acid that sits over on the left-hand side with the DI water and the drain pot, okay? And that DI water or that hydrochloric acid is very important because that hydrochloric acid is going to be added to everything. And that hydrochloric acid is going to be added to my standards. It's going to be added to my samples. It's going to be added into the rinse chamber when I try to regenerate my catalyst. There are multiple uses for that hydrochloric acid, and we've talked about some of those already. The issue here is that it's not concentrated hydrochloric acid. It is 1 molar hydrochloric acid. So if you are working in a laboratory like us, we never order 1 molar that's pre-made because we are buying for water and we just simply don't want to do that. We can make our own 1 molar whenever we have to. So we normally make the 1 molar from the 12 molar concentrated hydrochloric. So hydrochloric acid straight from the bottle in its fully concentrated form is going to be 12 molarity. That is the strength that's assigned to that acid. And we do not need a 12 molarity. We need a 1 molarity in order for this machine to use and for this machine to run. So I'm going to have to weaken it down. Think of yourself as a bartender, okay? Bartender, this is your alcohol from the shelf, and this is no mixers included. And you've just had a mixed drink order, and you need to dilute that alcohol down into a mixed drink so you can give it to someone that's there at your bar or there at your restaurant. So we need to kind of learn maybe the basics of how to do this dilution step. And the dilution equation looks like this. It's CV equals CV, where C is going to be the concentration of the sample or the acid or whatever I'm using, and V is going to be the volume that's going to be needed. All right, so the way that I solve this equation is it's CV equals CV. The concentration that I have in the beginning is a 12, and I want to know how much of that do I need to use in order to make a 1 concentration. So that is the concentration that I'm after, and we don't want to be wasteful, so we normally put in a volume here that we want to make. So let's just say 250 milliliters. So this is in milliliter, and this is in molarity, which means that this has to be in molarity, and it is. And that also means that when I solve for my answer, because 250 was in mils, my answer will also be reported in milliliter. The units are the same on both sides of the equation. Now, you don't have to just use molarity for this. Any concentration will work. Normalities, part per millions, part per billions, percentages, and so forth. And any volume will also work. So milliliters typically what we use, but I could also use liters here. I can use centiliters here. I can use microliters here. Any unit will work as long as it's the same on both sides. All right, so the way that I would solve this problem is 12 times x is 12x, and 1 times 250 is 250, and we're going to solve for x. So this is 12 times x, so you do the opposite of, which is divide, and you're going to divide by 12. So you can pop that number into the calculator to see what you get. You just put 250 divided by 12, and that will be the number of milliliters that you will need of the 12 molar, and you'll put that into a volumetric flask. That's 250, and then you will add up to the line with DI water, and you give it a good shake, and you give it a good twist, and now your mixed drink is all taken care of. So if you want to see that on the screen, just to double check your answer, it's going to be, let me click it, 250 divided by 12 equals 20.83. So you're going to take 20.83 milliliters of your 12 concentration, and you pour that into the volumetric flask, and then you add water until you get to the top of that line. Put a cap on this thing, you give it a good shake. They tell you invert it 30 times if you really want to be prim and proper. And then that is a well-mixed solution that is now a 1 molar and not a 12 molar. You've just diluted your first liquid, okay? And in this case, an acid. So I kept telling you along the course of these videos that hydrochloric acid is very important. And it's important that we add it to our samples for a specific reason. And I kept telling you, we'll get to that, we'll get to that, we'll get to that. Well, here is why we add hydrochloric acid to those samples. It helps me remove all of the inorganic material that might be there. So keep in mind, this is a TOC instrument, total organic carbon. And I am not wanting to measure the inorganic carbon, all right? So the hydrochloric acid is added to these samples and it's added to the standards so that way we can remove all of the inorganic carbon that might be present. I want my organic carbon only to remain behind. So what happens is that the hydrochloric acid targets mainly the bicarbonate and the carbonate ions from most of these inorganic substances. That's the one that's the most common. That's the one that we talk about the most. Remember, this is going to be hopefully a very small percentage of my total carbon. It might be, it might not be. That just really depends on the sample. But the acid will target the bicarbonate carbonates and it will remove them from your sample and your standards. Now, how does this process happen? Well, up here at the top of the screen, what you're going to see is bicarbonate and carbonate structures. So if you have a carbonate structure, this is just simply CO3. Okay, that's carbonate, CO3. If you add some acid, and in this case hydrochloric, that's what the H plus represents, you can make bicarbonate. And bicarbonate is CO3, but it has a H in front. So that carries a -1, this carries a -2. Well, if I add even more acid to that, I can get more acid to add in, and that acid, the additional acid, will make what we call carbonic acid, which is H2CO3, and now that is neutral. The issue here is that carbonic acid doesn't stay around very long. It likes to break down and it decomposes on itself. So this H2CO3 will break down, and it breaks down into water and guess what? Carbon dioxide. Well, wait a minute here. You just said that the TOC instrument measures carbon dioxide. And if we add acid to the sample, then that sample has carbon dioxide that will be generated. So wouldn't that be detected in the TOC instrument? And the answer is you're thinking, all right, but not quite. Okay, so what does that mean? All right, well, here's my syringe, right? And this syringe had the air line that's coming in through the side. And in this syringe, I have got my sample, and I have added a little bit of acid. That acid that we now know is hydrochloric will react with all of the bicarbonate and carbonate that will be in my sample at this point. So it is going to react with all of the inorganic carbon that might be present. I don't want to measure that. I want to measure total organic carbon, not inorganic carbon. Well, the purpose of the acid, as you saw in the previous slide, it's going to take the carbonates and it will take the bicarbonates, either one of these, and it will acidify them. We add acid, we add H, and it gives me H2CO3. That will then break down on its own, no help required, into CO2 and water. Water's not going to go anywhere. The water's going to stay in that sample, and that's okay because it's typically aqueous solution anyway. Who cares? But this CO2 is what you might have had the question on. Well, how on earth is this possible? Right? I've generated CO2. My machine's going to see CO2. Wouldn't this just see the inorganic as well? And the answer is no. And the reason is because we have air going into this syringe. And air is bubbling up through this syringe. And the whole purpose of this step is to purge all of the volatiles out and anything that will go away. So the air will purge the initial round of CO2 up and out of the syringe, and it never will be seen by the NDIR detector. The reason that this works is because what I will have left over is my sample. My sample will then go over into the combustion tube. And here is where my sample generates CO2. So what's happening is that the addition of the acid liberates all of the inorganics by generating carbon dioxide. And that carbon dioxide is getting pumped out of the system in the very beginning. So all of my inorganics go away. I no longer have to worry about this piece of the puzzle. Then my remaining sample is sent to the combustion tube. And at that point is when my organic material that didn't purge out converts into CO2. And it's that CO2 that my NDIR detector is beginning to see. All right, that's how this process is a little bit different. So that is the importance of the acid. That is why we have to keep our acid fresh. We have to make sure that it's the proper concentration that's needed for my machine, because if it's not, then it cannot react with the ionic or inorganic carbons and pump them out of the instrument in the very beginning, in the initial step. That is what goes on. It does generate CO2, but that is pumped out of the machine, and then my sample is delivered to the combustion tube where my organic material makes the CO2, and it's that CO2 that the detector will see in the very end. All right, so that's how this process works, and that's why the addition of hydrochloric is so important. What's up next is a little bit of maintenance. We're talking about a couple of different pieces of tubing line now, right? So I've got this tubing for the dilution water, which goes into this 8-point valve, and then I have the acid tubing that goes into the 8-point valve as well. And in addition to that, I have this ASI, maybe this auto sampler tubing line that goes into the 8-point valve. All of that has to stay rinsed and it has to stay clean. Okay, and there is a very simple way that I can ensure that I can flush these tubing lines out. And I normally do this every day before I use it, and I normally do it at the end of my analysis run. So after everything has ran and been analyzed, before I shut the machine down, I just give it another good rinse just to keep those tubing lines completely clean. The way that I do this is I go into the software, and the software is going to have an option for me that says replace the flow line content. That is what this is called, right? Because these liquids, they're flowing, and they're flowing through the lines or the tubing on the inside of the machine, especially near the injection port. So it's going to focus on the acid. It's also going to focus on the dilution water, and it's going to flush those tubing pieces out, and it's going to help keep them clean, and it also removes air bubbles that might get built up. So if I'm replacing the hydrochloric acid bottle, or if I'm replacing the water bottle, then I've taken the cap off, I've taken the tubing out, right? And when doing so, I've also now incorporated possibly air into those lines. They were submerged down into liquids, but because I removed those bottles, they now possibly could have little air pockets or bubbles on the inside. So when I put those bottles back on with fresh acid and fresh water, one of the things, again, I normally do in the very beginning of my analysis run, and it's for this purpose, is just to flush out the tubing to keep it clean and flush out the tubing to get rid of those air bubbles that might be present. Very simple process. The only thing that you have to do is go to the software, click on the instrument tab again. You're going to go back down to maintenance. Here we've seen 0-point detection, and we've talked about it. Here we've seen regeneration of the TC catalyst, and we've talked about it. And right here, you're going to see an option that says replace the flow line content. And what it does is that it sucks up new water, flushes it out, and gets rid of it. It sucks up new acid, it flushes it out, and it gets rid of it. It doesn't go into the syringe. It doesn't really go anywhere else. It just gets pulled through those tubing lines, and then it dumps it out of the system. So that's a very good kind of maintenance thing that you should be doing on your end to keep the system clean, to keep the system with no air bubbles and fresh liquid in the very beginning of each and every single day before you run your samples. All right. So in the next video, I told you we're almost done. Okay. In the next video, we'll talk about this filter that's also found on the inside of the instrument, and we'll kind of wrap things up hopefully a little bit for you. So that way you're only looking at maybe 1 or 2 more videos, and we're over with TOC as far as theory, function, maintenance, and troubleshooting. So stay tuned. Don't leave me yet. You're almost finished. Just give me a couple of more minutes and you're good to go.